Hello, this is Dr. Joe Trout from the physics program at Stockton University. Today's lecture is on astronomical instruments. Here we see the artist's impression of the Hubble Space Telescope above the Earth. In this lecture, we'll discuss how telescopes operate, and we'll also answer some important questions such as, why do we want to place telescopes in space? Prior to the development of telescopes, ancient civilizations built observatories. Here we see Machu Picchu, which was built in the 15th century in Peru. Also shown is Stonehenge in England, which is a prehistoric site dating back to 3,000 to 2,000 years before the birth of Christ. These observatories were used to help keep track of celestial bodies and their movements. The main instrument used was the human eye. The history of the development of astronomical telescopes is about how new technologies have been applied to improve the efficiency of these three basic components: the telescopes, the wavelength sorting devices, and the detectors. Several people are credited with the invention of the telescope, but it was Galileo who, in 1610, used a simple tube with two lenses, which he called a spyglass, to observe the sky. The most important functions of telescopes are to collect the faint light from astronomical sources and to focus all the light into a point or an image. But before we talk about the telescopes, we should discuss light. So what is light? Light is a wave of alternating electromagnetic fields that moves at 3 times 10 to the 8 meters per second in a vacuum. Here we see pictured in the red arrows is a representation of the electric field, and notice it moves up and down. The magnetic field is perpendicular to the electric field, and it moves in and out of the page and is indicated by these blue arrows. Don't forget, this wave is moving very fast in the direction of propagation. So what is the structure of waves? Consider a water wave. So the dotted line is the undisturbed state, or we call the equilibrium position, of the water when there's no waves moving through. So it's the height of the water. As water waves move through, the medium, which is the water, moves up and down. The highest point it moves up is called the crest, and the lowest point is called the trough. And the distance from the equilibrium position to the crest is called the amplitude. The wavelength, denoted by the lowercase letter lambda, is equal to the distance between any two crests or any two troughs. The frequency is the number of waves that go by per second. Frequency is measured in hertz, which just means the number of waves per second. The period is the time for one wave to pass by. It's denoted by the uppercase letter T. Note that the frequency equals 1 over the period, and the period equals 1 over the frequency. Light waves with different wavelengths have different colors and different energies. Once again, the wavelength of light is the distance between any two crests or any two adjacent troughs. Different light waves with the same light wavelength are identical. One of the properties of light is that in a vacuum it moves at 3 times 10 to the 8 meters per second. But when it runs through other mediums such as water and glass, it slows down. So the speed of light in water is 2.55 times 10 to the 8 meters per second. And in glass, it moves even slower at 2 times 10 to the 8 meters per second. Physicists like to talk about the index of refraction, which is just the speed of light in a vacuum divided by the speed of light in a medium. The index of refraction is indicated by a lowercase n. The index of refraction in a vacuum is just 1. In air, it's about 1.003. That means that in air, light moves almost as fast as it does in a vacuum. In water, the index of refraction is 3 times 10 to the 8 meters per second divided by 2.55 times 10 to the 8 meters per second, or 1.33. In glass, the index of refraction is 1.5. Notice that the larger the index of refraction, the slower the light is moving through that medium. So in glass, it's at 1.5, and in water, it's at 1.33. It moves slower in glass than water. Since it moves differently, at different speeds and different mediums, what happens is when it transverses from one medium to another, the light actually bends. So here we see two indexes of refraction, N1 and N2, and N2 is greater than N1. So in the blue section, the light is moving slower. As it moves from the fast medium to the slow medium, it bends or refracts. Here we see light traveling through a chunk of plastic, and what you see is that when the light hits the interface between the air and the plastic, it bends. Because in the air it was moving very fast, and in the plastic it moves slower. Then as it leaves the plastic, it bends back again, because it was moving in a slow speed and then is moving at a fast speed. It's even more complicated than that. What we find is that different colors move at different speeds in a certain medium. Here we see the index of refraction for several types of glass that are used to make lenses. What you may notice is that at the lower wavelengths, the index of refraction is higher. And at the higher wavelengths, the index of refraction is lower. This means that the shorter wavelengths will move slower through the medium. And that's what happens with a prism. If we shine white light into a prism, we find that blue has a smaller wavelength and it bends more than the red does. And when it leaves the prism, it refracts again. So the blue light bends even more, and the red light also bends. So what we see is that we can see a rainbow from there. We find that violet light has a wavelength of about 400 nanometers. Green, about 500 nanometers. And red at about 700 nanometers. Lights with longer wavelengths are redder, and lights with shorter wavelengths are bluer. So what causes white light? White light is just the combination of all the colors combined. Light is an electromagnetic wave, and it's made up of oscillating electric fields and magnetic fields. Light, visible light, is part of the electromagnetic spectrum. So there's other waves that are electromagnetic waves. For instance, gamma rays, X-rays, ultraviolet rays, infrared, microwave, and radio waves are all part of the electromagnetic spectrum. Gamma rays have a wavelength about the size of an atomic nuclei, and X-rays have a wavelength of about the size of an atom. Visible light is about the size of protozoans. Microwaves about the size of a butterfly, and radio waves can go up to a kilometer, which is about 0.6 miles. The visible light is a very small part of those electromagnetic spectrum. And astronomers use all of these wavelengths, gamma rays, X-rays, ultraviolet light, visible light, infrared rays, radio waves, and microwaves to study the universe. The shorter the wavelength, the more energy a wave has. So for instance, gamma rays have a very tiny wavelength. And they're so energetic that when they pass through your body, they can actually do damage to it. You also know that X-rays can pass through your body, and we can collect the X-rays and record them on a photographic plate or record them by computer and tell things about your body, or if you get an X-ray in the dentist, you can tell things about your teeth. Radio waves have very long wavelengths and not much energy. This is good because we have hundreds of radio stations around us and we're constantly bombarded by radio waves, but it doesn't affect our body. If we look at visible light, violet is about 400 nanometers, and it has more energy than red, which is at 700 nanometers. So the shorter the wavelength, the more the energy. If we look at the most energetic to the least energetic, we start with gamma rays. These are emitted by radioactive decay and come from molecules such as cobalt-60 and cesium-137. We can create X-rays by taking an electron and we get it moving very fast and we have it collide with a metal target, and when the electron collides with the metal target, it gives off X-rays. The sun is a good source of ultraviolet radiation, and it's still pretty energetic because the wavelength is still pretty short. And this is what causes sunburns and skin cancer. Visible light is next. So as we said, 400 nanometers for violet and 700 nanometers for red. If we look at infrared radiation, what that is heat. Next comes microwaves and radio waves. As we said, that can go up to almost a mile, the wavelength of radio waves. These are generated by electronic devices, and in particular, inductor and capacitor circuits, or LC circuits. But astrophysicists and astronomers use all of these wavelengths to study the atmosphere. If we look at figure A, what we see is a visible photograph where we recorded the visible light from the constellation Orion. B shows a recording of the X-rays that come from the constellation. And the third picture shows an infrared photograph. So any warm body emits heat, emits infrared radiation. And we can use infrared glasses or infrared photography to measure the infrared radiation. Here, most of the radiation is coming from dust that's glowing around in this region. So here we see 3 tubes that are filled with 3 different gases: mercury vapor, neon, and helium. And we pass through a large electric current. And what we see is that the different gases glow in different regions, in different colors. And if we look at the colors, we can identify the gas that's inside the tube. So notice mercury is kind of bluish, neon's kind of reddish, and helium's on the purple end. Astronomers and physicists use this concept to figure out what stars are made out of. So for instance, if we were to fill a tube full of hydrogen, we could pass it through a prism, and the different colors would bend at different angles. So the shorter the wavelength bends the most, and the smallest and the largest the wavelength bends the least. So this is known as the emission spectrum and shown as the emission spectrum of hydrogen. So where white light would show a continuous spectrum, if we energize hydrogen gas, what we see is that 4 colors appear. And these 4 colors have 4 different wavelengths. There's violet at 410 nanometers, blue-violet at 434 nanometers, blue-green at 486 nanometers, and red at 656 nanometers. So if we take the light from the star and pass it through a prism and watch what colors appear, we can tell what the star is composed of. What happens is if we look at the planetary model of an atom, what the planetary model is that in the center, there's protons and neutrons. And orbiting outside of that are electrons. The more energy an electron has, the greater the orbit. So when we send the electric current through, the electrons gain energy and move to a higher orbit. Then they decay back again. And when they do, they can go to certain orbits. And when they decay back to these original orbits, they give off colors, or photons. And a photon is just a little piece of light. So here we see that there's 4 colors of photons that can be given off. And that gives us our emission spectrum. The energy of the light rays is inversely proportional to the wavelength. So the shorter the wavelength, the more the energy. So violet has more energy than red light because violet has a smaller wavelength than red does. So see if you can answer this question. In the constellation Orion, Rigel, in the lower right-hand corner, appears as a bright bluish star, while Betelgeuse, in the upper left-hand corner, appears as a bright reddish star. So Rigel is cooler than, the same temperature as, older than, hotter than, or more massive than Betelgeuse. So don't forget, the energy is proportional to 1 over the wavelength, and blue has a shorter wavelength than red. So the answer is hotter than. Since Rigel appears bluish, its wavelength is short, so it must be hotter than Betelgeuse. Really, everything from gamma rays to radio waves are emitted by the star. And we can use this information to find out how hot the star is. So we take the light from the star and we measure the intensity. And intensity is the amount of energy per area per unit time, or per second. So the light curve that's labeled as 600 Kelvin, if you see, its intensity peaks in the violet region. We call that white hot. Next, we have another graph of the intensities for a star that's burning at 4,000 Kelvin. That peaks around yellow. And if we look at another star, we see it's burning at 3,000 Kelvin. We call that red hot. And it burns at the red end of the spectrum. So we can use the wavelengths and the intensities to find out how hot stars are. Not all the wavelengths makes it to the Earth's surface. So the top graph shows the atmospheric opacity. So if something's opaque, you can't see through it. So if you think of the atmosphere like a window, then if it's 100% opaque, then you can't see through it. And if it's near zero opaque, or if it has an opacity of near zero, then it's almost transparent. You can see through it and light can travel through it. So here we see that gamma rays and X-rays don't make it to the Earth's atmosphere. The Earth's atmosphere is opaque to it. Visible light makes it to the surface. And that's how we can see each other. Infrared light, or heat, most of it is absorbed by the atmosphere. Also, I forgot ultraviolet. Most of it does not make it to the Earth's surface. Most of it is blocked by the ozone layer, or absorbed by the ozone layer. If we look at short radio waves, they do make it to the surface. So if we want to examine gamma rays or X-rays or ultraviolet light, we need to go out into space to observe it because it's blocked by our atmosphere. Visible light, we can use telescopes. For heat and for microwaves, they're pretty much absorbed by the atmosphere also. So we can't see them on Earth. They don't make it to Earth. So infrared spectrums have to be observed from outer space. Most of the infrared heat, or the infrared waves, are absorbed by water vapor in the atmosphere. Radio waves are observable from Earth, and we have special telescopes called radio telescopes that can observe the radio waves, and we'll talk more about these later. Just as a more graphical representation, if we think of the Earth's atmosphere as a thick window. For radio waves, the window is open and the radio waves can travel through. Infrared radiation, most of them are absorbed by the atmosphere, most basically by water vapor. If we look at visible light, the window is open and we can see it on the Earth. Ultraviolet, most of it is blocked high up in the atmosphere. X-rays and gamma rays, the window is closed. We can't see them on Earth. You can think of light as being spherical waves. So this is the idea. If you take a lamp and put it in the center of the room, it lights up the whole room in all directions. So you can picture these spherical waves moving away from the light source. When they're close to the light source, you can see that it's really easy to tell that they're spherical. But as you move further and further away, it's harder to detect that they're actually curves. And we call these plane waves. We like to draw light rays that show the direction of motion of the waves. And they're drawn perpendicular to the point of the wave. So that light ray shows how the electromagnetic waves are moving in what direction. So for example, if we draw light rays around the sun, they would be completely symmetric around the sun, and they move in all directions. I've only drawn a few in here. What you can notice is that light that comes directly from the sun hits the Earth. But the sun's very big compared to the Earth, and it's very far away. So any light waves that are even a little bit off, at a little bit of an angle off a direct path to the Earth, miss the Earth. So what we say is that the light waves coming into the Earth are all parallel. They don't cross. Because if the light ray was even just a little bit of an angle off, it would just miss the Earth. Remember we talked about light bending as it moves from one medium to another? This is really a pretty cool property. What we can do is, for instance, create lenses. And what happens with the lens is that if we take parallel light rays coming in, they'll converge at a point, and this is called a converging lens. If you remember, if you were younger, if you ever had a magnifying glass, you may have found that if you point the magnifying glass at the sun, you could form a really bright little white dot. And you can even burn holes in leaves or paper. So a magnifying glass is a converging lens. It takes all the light and it converges onto a point. This point is known as the focus, and the length from the lens to the focus is called the focal length of the lens. Convergent lenses are used in many things. For instance, the human eye uses a converging lens. It takes light rays from, say, a tree, and it bends them and forms a little image on the back of the eye where there's nerves that are sensitive to the light. They react when the light is hit and produce a little voltage that they send to your brain and tell you that that's a tree. Notice that the image of the tree on the back of your eye is upside down. It's actually inverted. So this is one of the properties of a converging lens. Cameras work the same way. They have a converging lens, and they have an aperture which defines how much light you let into the film. Once again, the converging lens of a camera produces a smaller inverted or upside down image on the film or on the CCD, the charge coupled device, which is used, for instance, in your phone. And we'll talk more about that later. And refractor telescopes also use a converging lens. So they take a faint amount of light that's parallel, that's all coming in from a star, and then it converges that light onto a focus. And we end up with a smaller upside down image of the star. Mirrors can do the same thing. So spherical mirrors, they're really parabolic, but spherical mirrors, if light rays come in parallel, they'll reflect and all pass through at the focus. Reflector telescopes used a curved mirror. So they take parallel rays coming in from the star where it says light enters here. They hit this curved mirror, and this is a concave mirror, and they produce a smaller inverted image. There's also a secondary mirror, and that's used to take the image and reflect it into something called an eyepiece. And the eyepiece is just a magnifying glass which enlarges the image. So there's two main types of telescopes, reflector and refractor. Reflectors use mirrors to focus the light, and a refractor uses lenses to focus the light. Both of them create an inverted, smaller image. And to make the image larger, so we can see it with our eye, we use an eyepiece, which is just a magnifying glass. One thing to note is that secondary mirror in the reflector, it doesn't cause you to have a hole in the picture. So it's not like you'll see a picture of the sky and then there'll be a black circle in the center caused by that secondary mirror. It still gives you a full picture of the sky. So if we take a concave mirror, we can make a telescope, and any light rays that come in parallel go to the prime focus. With a Newtonian focus, we use a secondary mirror and send the light out to the side of the telescope just because it's more convenient, and we can put the eyepiece there and magnify the image, and it's easier to operate the telescope. The Cassegrain focus, instead of having the image focused on the side, through the side of the telescope, there's a hole in the concave mirror, and it sends the image through that hole. Once again, there isn't like a black spot on if you were to take a picture, there wouldn't be a black spot caused by that secondary mirror. You still get a full picture of the universe. So how do telescopes work? The main job of a telescope is to collect as much light as possible. Really, they're just buckets to collect light. The bigger the bucket, the more light you can collect. If we look at the area, it's proportional to the diameter squared. So 2 times the diameter, 4 times the area. 4 times the area, 4 times more light. So each time we double the diameter of the mirror or lens, we get 4 times the amount of light. We'll also see that bigger telescopes can see fainter objects, which are usually farther away. Bigger telescopes also have better angular resolution or picture clarity, and the magnification is better for bigger telescopes. Objects appear larger and brighter. So when we talk about the picture quality or the angular resolution, consider this. Here's two stars, S1 and S2, and they're separated by some angle. And they go through the aperture of the telescope. And we see that there's a smaller inverted image is produced. So don't forget, on the image, star 2 is on the top and star 1 is on the bottom. If these stars were moved closer together, what would happen is their images would be closer together. But eventually, they would overlap and we wouldn't be able to tell that they're two stars. So this minimum angle between the two stars is equal to 1.2 times the wavelength over the diameter. So the larger the diameter, the smaller this angle can be, and the better resolution we have. So here we see pictures with decreasing resolution. So the top picture shows two stars. And the middle picture isn't as good of a resolution, and the stars are starting to merge together, the image of the star. And finally, we can't even tell it's two dots anymore, or two stars. So here shows two images. The bottom image was taken with a telescope that's twice the size of the top image. Notice how much more detail we get. We can actually see more stars and more detail, and we get more light, and the picture quality is clearer. And here we see 4 different telescopes, and each one is bigger, going from A to D. So the diameter of the mirror or the lens is bigger, and you can see how the quality improves every time we get a larger lens or mirror. Most of the modern telescopes are reflectors. So images can be formed either through reflection or refraction. There's some problems with each of these models, but there's fewer for reflection telescopes where we're using mirrors. First, reflectors suffer from something called chromatic aberration. When you think of chromatic, you think of color. So this is something to do with colors. Don't forget, the index of refraction is different for different wavelengths, which means that the wavelengths are going to bend by different amounts. So violet bends more than red does. And we can reduce this effect by the choice of materials and the design we use. Mirrors don't suffer from this defect. So this is what happens. Light passes through the lens, and violet or blue bends more than red does. That means that blue and red are going to have different focal lengths. So if we focus on the red, the blue will be out of focus. If we focus on the blue, the red will be out of focus. And this is known as chromatic aberration. Mirrors don't suffer from this, but lenses do. Another problem we have with making images is called seeing. What happens is as light travels through the atmosphere, if you think about it, the atmosphere isn't uniform all the way out. So for instance, there's different amounts of water vapor. So as it travels through the miles of atmosphere, the light refracts one way and then it refracts another way. And what we end up with is we can see a blurry image. Once again, this is known as seeing. If there's good seeing, that means there's not much water vapor in the way, and we can see really well, and we get good pictures. If the seeing is bad, then we get lots of refraction over and over again through the atmosphere, and it smears out the image. Another problem with refractor telescopes, they use lenses only, is that some light is absorbed by the glass. This is a small problem, but it's not a problem if you have a reflector telescope. Also, large lenses are quite heavy. So the larger you make the lens, you can only support it on the outside, and what will happen is that the lenses begin to become deformed by gravity because they're so heavy, and they can only be supported by the outside, by the edges. Mirrors can be supported from the back, so you can make huge mirrors and not have this problem. Lenses have two surfaces and mirrors only have one. That means you have to do twice as much work, right? We have to machine it and polish it. And with mirrors, we only have to do one surface. So as a summary, most modern telescopes are reflectors. Light traveling through lens is reflected differently by different wavelengths and produce a chromatic aberration. Some light traveling through the lens is absorbed. Also, there might be tiny bubbles in the lens that also cause it to refract. Large lenses can be heavy and can only be supported by the edge. And finally, lenses need two optically acceptable surfaces. Mirrors need only one. Modern telescopes are reflectors, and reflectors do have some problems. That secondary mirror, although it doesn't produce a hole in your image, does cause about 10% light loss. By the way, mirrors are really parabolic, not spherical, but it's easier to think about a spherical lens, a mirror. Okay, so this is how a refracting telescope works. We take an objective lens, and it's a converging lens, and it takes parallel rays from the sky, from the star, and it produces a small inverted image. So the image is smaller than the star, and it's inverted, it's upside down. Then we take a magnifying glass and magnify the image. So the objective lens produces a small image. This is what we call a real image, by the way. And then the eyepiece, which just magnifies the image formed by the objective lens, this image is called a virtual image. With a concave mirror, we also see that the object produces an image that is inverted and smaller. And then once again, we use the eyepiece to magnify that image. This is a tiny problem because, for instance, if you're looking at a star and you want to move the telescope and you think you should move it up, you'll actually have to move it down, right? Because the image is inverted. And if you think you should move the telescope to the left as you're viewing through it, you really want to move it to the right because everything's inverted. How do you buy a telescope? Well, get the biggest that you could afford. And a 4 inches minimum is important. Ignore the magnification because you're going to use different eyepieces to produce different magnifications. So buy 2 or 3 eyepieces. The reason for this is maybe you get an image of the moon, and maybe you want to look at the whole moon. Then you'll use an eyepiece with a small magnification. But then say you want to look at one of the craters on the moon, you'll use another eyepiece with a larger magnification. Also, look for an equatorial mount. And it's good to have a finder scope, which will help you maneuver the telescope and help you put it into focus easier. Probably $500 is the least you can spend. And for pictures, you need more money, and you need a tracking motor and a camera adapter. Cameras, like the one on your cell phone, use charge-coupled devices to record the image. What these are pixels, and they are electronic devices that are sensitive to light. They produce a little voltage when light strikes them. And you can see they're in this checkerboard pattern, and there's some for red, green, and violet or blue. Before cameras, we had to use film or photographic plates to record the image. This was a problem. We find that charge-coupled devices can record 75% of the photons that strike, and photographic plates can only do about 5%. This means with a CCD camera, we can record objects 10 to 20 times fainter or record 10 to 20 times faster. The reason that this is important is that the Earth is moving. So as we're taking pictures of the star, the Earth is moving, and it would blur out the image. So what we have to do is keep moving the telescope to record enough light to get the photograph to take. But now with the CCD cameras, we can record 10 to 20 times faster. And we can also save it on a computer very easily. When building an observatory, and this is something that houses the telescope, what are the three important things? Location, location, location. What these domes do at the top of the observatory is the domes move in a circle, and they open up the roof so that you could point the telescope out towards the stars. Don't forget we have seeing, which is atmospheric turbulence causing eddies of swirling air, and the light's refracted over and over again, causing the shimmering or twinkling of stars. Sometimes you can see it with the naked eye. You look up to the skies and it looks like the stars are twinkling. This is due to the atmospheric turbulence, or seeing. So it would be nice if we could put a telescope high up in a mountain. That way, we wouldn't have to look through so much of the atmosphere. Here we see a large telescope mirror, and this is one of the primary mirrors of the European Southern Observatory's very large telescope. See the people standing next to the mirror, and you get some idea of how large this mirror is. It actually is about 8 meters. And if you figure you're roughly 2 meters tall, then it's 4 times your size in diameter. Here we see the Palomar 5-meter reflector. And we also see the Gemini North 8-meter telescope. Notice the designs are very different. For the Palomar, the tube is completely enclosed, and for the Gemini, the tube is pretty much open. The Gemini mirror does sag a bit, but with modern computers, what happens is it's possible to measure this sag many times a second and apply forces at 120 different locations and bring them back and to correct for the sag of the mirror. This process is called active control. Also, 36 eyes are better than one. So instead of having one giant mirror, what happens here with the Keck telescope is that there's actually little hexagonal mirrors, and they're all attached to one another. If you look really closely, you can see the hexagons in the mirrors. One of the greatest scientists in the history of astronomy was George Ellery Hale, and Hale's work led to the construction of several major telescopes: a 40-inch refracting telescope, and 3 reflecting telescopes, a 60-inch Hale, 100-inch Hooker telescope at Mount Wilson Observatory, and a 200-inch Hale telescope at the Palomar Observatory. Here shows the world's largest refractor, and it's the Yerkes 40-inch, so it's about 1 meter size lens. Imagine how thick and heavy that would be. So we want these observatories to be high up in the mountains. And what that is going to do, and specifically if we get high up in the mountains in the desert. So if it's in the desert, we know it's not going to rain many nights a year. And also, if it's high up in the mountain, we have less of the atmosphere for the light to travel through. We can also now use adaptive optics now that computers have become so powerful. So we understand how the image is going to get deformed, and we can tell the computer how to correct for this. So one of the clearest pictures of Jupiter ever taken from the ground, this image was produced by adaptive optics using an 8-meter diameter telescope at the Very Large Telescope in Chile. The adaptive optics uses infrared wavelengths to remove the atmospheric blurring, resulting in a clearer image. Here we see the charge-coupled devices, or part of it, and this is the CCD, is a mere 300 micrometers thick, thinner than a human hair, and it holds more than 21 million pixels. The higher number of the pictures, the better the picture, and the better the resolution. We also like to look at the infrared information from stars. So what you can see here is that if we look at, here's a man with his hands inside a black plastic bag, and we can't see the person's hands. But if we use an infrared camera, it can see the heat coming from the person's hands, and we can now see their hands. So we use this infrared information in studying the atmosphere. We also use a prism spectrometer. So as the light from the telescopes passes through a slit, and then a prism, or a grating, disperses the light in the spectrums, and then it's photographed or recorded electronically. We also use radio waves coming from stars and planets. And this rotating radio antenna was used by Jansky when he found out about the radio radiation from the Milky Way. And here we see a radio image. So we record the radio waves that are coming in, and we can produce an image. And these colors represent the intensity of the radio waves coming from, in this case, Cygnus A. Radio telescopes look like communication dishes, right? Like satellite dishes. And they can record and they're just concave dishes that reflect the radio waves to a point. If we want better resolution, we can use a whole bunch of these. So this shows the Atacama Large Millimeter Submillimeter Array, or ALMA. And it's located in the desert in northern Chile. Here we see the very long baseline array, and this shows the distribution of 10 such antennas, or radio telescopes, stretching across the United States. The largest radio and radar dish is a 1,000-foot radio dish filling the valley in Puerto Rico. So it actually was a natural valley, and they smoothed it out and made it optically sensitive to radio waves, and that's now the telescope. If we want to look at infrared information from stars, we can use SOFIA, or the Stratospheric Observatory for Infrared Astronomy. So here shows some infrared images of a region of star formation and the remnants of an exploded star, and a region where an old star is losing its outer shell. So using infrared information, we can gather information about the life cycle of stars, and we'll talk about that in a couple of chapters. If we place telescopes in outer space, we don't have to worry about the atmosphere at all. And we can see all of the wavelengths from gamma to radio. We can also look at the X-rays. So we also look at X-rays of the universe to determine some information about the stars. This is Sandra X-ray satellite, and it's the world's most powerful X-ray satellite. Before these telescopes go into space, sorry about that, they go through some testing known as cryogenic testing, where they expose the mirrors to extreme heat and gather accurate measurements of the changes in their shape as they're heated and cooled. So why do we want telescopes in space? There's no seeing. We don't have to worry about the atmosphere. And all the wavelengths of light can be seen. The Hubble Space Telescope is at least 10 times finer resolution than existing Earth-based telescopes. It has 30 times greater sensitivity to light. Initially, when it was sent up, it was too flat by about 2 micrometers, about the width of a human hair. And then in 1993, a repair mission was sent up that put on new gyroscopes, better solar panels, and new sets of mirrors to compensate for the faulty primary focus. So if we consider ground-based telescopes, they can have bigger mirrors, they cost less, and they're more stable. The cons are that they have seeing and that we have to worry about the atmosphere, so they can't see all the wavelengths. For the space-based pros, there's no seeing, so we don't have to worry about the atmosphere, and it can see all kinds of light. The cons, of course, is that they're expensive, and we have to use smaller mirrors. So here's an artist's conception of the European extremely large telescope. The primary mirror of the telescope is 39 meters across. So remember, you're about 2 meters tall. So it's 20 times your height is the diameter of the mirror. So let's finish up with some key terms. First, we have adaptive optics. These are optics that can compensate for distortion of the image introduced by the atmosphere and result in sharper images. We have the aperture. That's just the diameter of the primary lens or mirror. The bigger the aperture, the better the telescope. We have charge-coupled devices. These are arrays of highly sensitive electronic detectors of electromagnetic radiation, and they're used at the focus of the telescope to record the image or the spectrum. We have chromatic aberration. This was the distortion caused of an image that they appear to be fuzzy because each wavelength coming through the material focuses on a different spot. A detector is just a device sensitive to electromagnetic radiation that makes a record of atmospheric observations. The eyepiece. The eyepiece is what magnifies the inverted small image that's produced by the objective lens or by the mirror. The focus is the point where all the rays converge by a mirror or the lens. Interference process in which waves mix together such that their crests and troughs can alternately reinforce or cancel each other out. An interferometer is an instrument that combines electromagnetic radiation from one or more telescopes to obtain a resolution equivalent to that would be obtained with a single telescope with a diameter equal to the baseline separating the individual telescopes. An interferometer array is just a combination of multiple radio dishes. The prime focus is the point at which the telescope would focus all the parallel light rays coming in. Reflecting telescopes, telescopes that use mirrors. Refracting telescopes, telescopes that just use lenses. Resolution is the detail in an image. The larger the diameter of the mirror or lens, the better the resolution. Seeing is the blurring that occurs due to the unsteadiness of the Earth's atmosphere. And a telescope is an instrument for collecting visible light or other electromagnetic radiation. So that ends today's lecture, and I hope you learned a little bit about telescopes, and thank you for your attention.